Okay, so this topic is the data encryption standard, which the DES traces directly to both of the cryptographic technologies that are within Bitcoin. And I think you take DES and you can compare it to the Enigma. When you do it that way, I don't think it's easy to wrap your head around what DES is. So that's why we're covering DES, and we're going to use the Enigma to show this problem here of linear equations, and then tie that into how DES solves that problem, and then how DES works. So we're going to start with Claude Shannon. This is the father of mathematical cryptography. He had a deep understanding of how computers worked. He was also very familiar with the Enigma. He was familiar with the principles of cryptography, and he was friends with Alan Turing as well. He described the problems of the mechanical cryptographic devices. He described the problems with the multiple alphabet cipher methods, with the Enigma and all the other similar mechanical methods. He looked at it from a process point of view. You take a plain text, you go through a process, you get a ciphertext. But within this process, there are inherent functions. And this function is just going to be based on the number of input settings that you have. So for a simple multiple alphabet cipher, your ciphertext output here is going to be a function of your corresponding plain text plus a handful of secret variables or a handful of secret settings. And same for the more advanced Enigma. From your ciphertext here, there's a direct link from this letter all the way back to your plain text. So there could be a lot of variables that are changing it, but it's still a direct link based on a linear equation. This direct linear relationship between your ciphertext and your plain text. And so that is the first problem, is this linkage. And then the second problem has to do with all of the patterns that we know about in the English language. So an attacker doesn't know the plain text, but there are countless patterns that are generally known, and you can make assumptions about what the plain text is. So in the other videos, we showed how multiple alphabet ciphers removed patterns, but really the pattern is it's just hidden. The pattern is only hidden, and there's still that direct link. There's still the pattern inside of the ciphertext. So now we're going to combine these two problems, and here's how an attacker can go about it. An attacker can just use context clues and create guesses on what plain text combinations are, what plain text is statistically likely based on what's all known about the human written language. And we can generate enough guesses, educated guesses, and we have enough of the linear equations, and it doesn't matter how many secret variables there are. At some point, we reach this algebraic setup to where we have a certain number of unknown variables, and then we have a certain number of linear equations based on those variables, and then once they are the same, you can now solve for these equations. And there's going to be a little bit of cycling going through here. You might have to try a few different words and a few different guesses, but the brute force approach you have to do can now be highly informed by the known patterns. And in the mechanical days, even this algebraic approach was sufficiently very difficult. This is the machine Alan Turing built to defeat the Enigma. It was a monumental effort to do this brute force attack. But when you have computers looking at this problem, electric computers, solving a problem like this would be completely trivial for modern computers to do. And Shannon was the first to at least get the recognition on this idea and this problem. So for cryptography going forward in the computer age, there had to be this breaking of linearity. You had to remove this link from your ciphertext to your plain text. He didn't know how to do it, but he knew the problem, and he described it as confusion. So now on to the second piece of the problem is getting rid of all the language patterns that are known. This was the two-part problem that was described by Shannon as what computer age cryptography would have to do. Otherwise, the logic attacks are going to be too easy. So when we look at DES and what DES does, DES is solving these two problems. It's removing the linearity, it's removing patterns. And just for a little extra context, here's the internet. It came around shortly after the invention of the silicon chip. And once we had the internet, so we had ATMs, we had banks, there was this demand for new cryptography was right on its heels. And then up here we have DES. The key component of DES is something called the Feistel function. When it was first invented, it was called the Lucifer function. But this was developed and then matured over many years and then eventually published as DES. And DES is still, there are still flavors of it out today. It's still in existence. And just a quick side note, we're not going to cover this. The one-time pad also solves these two problems, but making keys and distributing keys for the one-time pad are very cost prohibitive. So there's only a few situations where it's used, and these situations have the right cost benefit. And back to DES. So this was the first computer internet era encryption and decryption construct. And we're going to go through these concepts that it used. These concepts are still commonplace. These are the foundational cryptography concepts. So now for how they work. And this is a picture is the official DES process, what it looks like. And we're going to take this step by step, one step at a time. So the first thing we have in our process is the plain text is going to be broken into 64-bit pieces. And then these pieces are going to get passed through DES one piece at a time. And we also use a 64-bit secret key. And you see these two different segments here, this left and right. You can see this is some crisscrossing. This is just so DES is invertible. So I'll show you what it looks like here. You can use DES with the secret key and plain text. You're going to get a ciphertext message. And now I'm going to invert this process so it's like a mirror image of itself. And you can see it looks basically the same. So then now you can take your cipher message and your secret key, go through the inverse of the process, and you're going to get your plain text back. So the left and right and the crisscross look confusing, but it's giving you the inverse to get back the plain text. So it's just making DES simpler to use. So now we're going to walk through what happens as we take our input. And the first thing that happens is this shuffle. All 64 bits are going to go through a shuffle. And the shuffle is also split in half. Only 32 bits from the right-hand side are going to take the next steps. And these 32 bits go through the start of the Feistel process. These are the 4 steps of the Feistel process. Step 1, these 32 bits are going to be expanded into 48 bits. And this is a standardized way of expanding these. Then with these 48 bits, we're going to add in a key. More on the key in a minute, but here we have 48 bits from our 64-bit secret key. We insert the key, we do a standard XOR function, and we're going to get these 48 bits as an output. This output is now going to be our input for the next step, which is the substitution. So we have, on top here, we have groups of 6 bits. Each group of 6 bits is going to go through a substitution table that reduces it back down to 4 bits, bringing us back to a total of 32 bits, ready for the next iteration. Each substitution table is also defined in the DES process, and we're going to just do an example here. So in our example, this 5th group of 6 bits, here they are, they're going to pass through this substitution table, and we get a 4-bit output. So a couple of things to notice about what the table looks like. In each row, you're going to see there are no repeat outputs. And it's this idea is what breaks the linearity for each individual bit. So in our output example, 1100, you can also find this output in each of the other rows. So you take any one of the output bits and you try to trace it back to any of its possible input bits. What you find is in each S box they're gonna look a little different in each S box, but the idea is the same. Where the cumulative effect is you have a 50-50 chance. Each output bit has a 50-50 chance of being either a 0 as the input or a 1 as the input, and that's what's breaking the linearity. And there's no equation to this. This is chance. This is a 50% coin toss. And this is just for okay, so now back to the start of the substitution. This is just for an individual bit. And there are many other design criteria that go into these S boxes. And this is what solves the first piece of the problem. These S boxes are breaking the linearity. They're replacing linearity with a 50% chance, a coin flip. And now we're going to move on to the second piece of the problem, which is removing these patterns in the ciphertext. So in the next steps, after we substitute, we shuffle again. Then we repeat that entire process. This substitution and iteration over and over and over again is what's going to, this shuffling followed by an iteration of the whole process over and over and over again is what creates what's called the avalanche effect, which removes patterns. So we've gone through, looking at it a little different now, we've gone through, taken our 32 bits, we've gone through the expansion, we added a key, we went through substitution back down to 32 bits, and then after that we do another shuffle again, which is going to obviously shuffle around our bits, and then now we're going to start the repetitions. So we're here now in the process. We just finished our first iteration. We are on our way now to the second iteration, and this crisscrossing here and this XOR, this is essentially, think of this as just more shuffling that's going on. And these XOR combinations are bringing in all 64 bits of this plain text that we're dealing with now. So it's more shuffling, and we're going to start the second iteration. This is iteration 2. Expand. We get a new key. We have a new key. And take a quick pause and do the key schedule. I won't spend too much time on it, but each key goes through a shuffle where 8 bits are taken out, and every iteration is going to only use 48 bits, and there's a little shift that goes on for each key that's used. That's all there is to the key creation for each round. So now we had the next round and its key, and we go through this round again. And the big point here is just back to this shuffle now. It's just back to this shuffle, where this shuffle makes sure that after the substitution table, all of these bits are to get shuffled, which means they're going to see a different S box during their next iteration, a little different flavor of linearity breaking. And then each bit is also going to be influenced by the key again before it goes off to see a different S box. So this is very intentional, as this whole ordeal is going to repeat 16 times. So every bit is going to do every flavor of S box. Bits are going to see a different flavor of S box, and this shuffling also, though, creates this kind of explosion of bits that are going to occur, and this explosion is called the avalanche effect. And we're going to look at a website right now where we can see this avalanche effect in action. Okay, so this is the website. This is essentially a website that's going to emulate or simulate the DES process. So I'm going to put in a piece of data here. This is a demonstration of the avalanche effect. So and I've got the result here. We'll take a closer look at this here in a second. But now I'm going to change just this one piece of the input. I'm going to change it from a C to a B. Just that one change in the input. And I'm going to run the DES simulator again. And now our result is something that is entirely different. And now we'll take a closer look at what happened here. So the difference between the B and the C is just a 1-bit change. But the first time we ran it using the C spelled correctly, that was the output. When we change it from a C to a B, this is the output. So just this one change exploded the output. So this output is because of the shuffling and the substitution boxes, the output is every individual item in this output is linked to every individual input item. There's no direct connection. There's no one-to-one connection. So it's the explosion, the avalanche effect is what solves the second piece of the problem. So where each individual output has been impacted by every single input. So there is no longer this linkage between any one input bit and any one output bit. There is no more pattern. So finally, we've removed all the linearity. We have scrambled all the patterns. The only option left takes our attacker back to this infeasible brute force option. So the concepts of shuffling, substitution boxes, doing this over several iterations, these are the foundational concepts that of the internet and computer age security.